Okay, calculus 12.3 is applications of derivatives. And you can probably see this coming, velocity and acceleration. As an object moves along a curve in the plane, coordinates of its x and y, coordinates of x and y of its center of mass are each functions in time. Rather than using the letters f and g to represent these two functions, it's convenient to just write x and y as x of t and y of t. So the position vector r of t takes the form of x of t plus y of t, x of ti plus y of tj. Find the corresponding velocity. Do exactly like we did in Cal 1. We take the derivative. To find the speed, since of course speed is just a number, velocity just not only gives the speed but direction. And then to find acceleration would be the second derivative. Speed is just the magnitude of our velocity, which would be the square root of the sum of all the velocity values squared at that point. And anything that applies to 2 dimensions is also going to apply to 3 dimensions. So we've got velocity is the first derivative of the vector value function, acceleration is the second derivative, and speed is the magnitude of the velocity. To find the velocity, the speed, and acceleration vectors, velocity vector, acceleration vector, and then the speed for the particle moving in a given plane or space curve. So we've got r of t equals 2 sine of t over 2i plus 2 cosine t over 2j. Means the velocity vector is the derivative. The derivative of 2 times sine of t over 2 is cosine of t over 2. Derivative here should be negative sine t over 2. My acceleration is just the derivative of that. Should be negative 1/2 sine t over 2. This next one should be negative 1/2 cosine of t over 2. Now the speed. It's the square root of these two things squared, so that's cosine squared t over 2 plus negative sine of t over 2 squared, which is square root of cosine squared t over 2 plus sine squared t over 2. Cosine squared plus sine squared is 1. Square root of 1 is 1. Now anything that happens in 2 dimensions can also happen in 3 dimensions. First derivative of 2t squared is 4t. This is 4t to the negative first, so it'll become positive 4 over t squared. Third one becomes 8 over t. Acceleration. The next derivative, 4. This is 4t to the negative second, so that should become negative 8 over t cubed. And this one should become negative 8 over t squared. Now speed. So all of these things have to be squared, so that's 4t squared plus 4 over t squared squared plus 8 over t squared equals the square root of 16t squared plus 16 over t to the 4th plus 64 over t squared. There's nothing else we can really do there. So that's it. Now, what does this help you do? You now have the machinery to derive the parametric equations for the path of a projectile. Assume gravity is the only force acting upon the projectile after it's long. No wind resistance or anything like that. So the motion occurs in the vertical plane, which can be represented by the xy coordinate system. For a projectile of mass m, the force due to gravity is F equals negative mgj, where acceleration due to gravity is 32 feet per second, or 9.8 meters per second By Newton's second law of motion, the same force produces an acceleration and satisfies the equation F equals mass times force equals mass times acceleration. Consequently, the acceleration of the projectile is given by mass times acceleration equals negative mgj, which implies a equals gj because m is still mass. Now, we can use acceleration generally to find other vectors by integrating. A projectile with mass m is launched with an initial position of r0 and initial velocity v0. Find the position vector as a function of integrating. All they're asking you to do is take your acceleration function, which is negative gj, and integrate it with respect to t. So that would be negative gj is constant t plus c. C is the v0, because when t is 0, it's our initial velocity. So if v of t equals negative gjt plus v0, something we can do with v0 is we can break it into its components. Any direction is going to have an angular component where there's a cosine direction and a sine direction. Since this is j, it's vertical, gravity, we can take our initial velocity and break it up into its components. The horizontal component plus the vertical component, which will allow me to distribute the v0. I'm going to put the v0 cosine theta. I'm going to put my I first. Now these two are both j terms. So we have minus gt j plus v0 sine theta j. Keep that in mind. And now when I integrate again to get to the position function, I get the integral of v0, which is initial velocity, is a constant cosine theta. It's relative to t, so it'll be v0 cosine theta t I. This is relative to t, so it'll be minus 1/2 gt squared j plus v0 sine theta t j. So this one's exactly like the cosine one because it's not relative to t currently, plus our initial position, which we'll call d. However, this thing is our initial height, so our initial height should be in the y direction, so we'll call it r0 j. So this whole thing is v0 cosine theta ti plus a whole bunch of stuff times j. I'll write it down here. Negative 1/2 gt squared plus v0 sine theta t plus h, all times j, where h is our initial height. Now, in many physics problems, you aren't necessarily given the initial velocity and position vectors. Instead, you're given the initial height, the speed at which something was hit, the corresponding angle of the launch. And so by breaking up your speed into corresponding vectors using sine and cosine, we can get the following general, usefully pieces of information. The initial position is the height in the y direction, so j. Initial velocity has an x and a y component where it's Pythagorean theorem, so it's v0 cosine theta I plus v0 sine theta j. This means the position vector from above can be clarified, which we did it along the way anyway, and we can reorganize, which we did up above. And we will finish the one problem in 12.3 and start 12.4 in the next video.